Hello, Math 300, and this is Professor Gonzalez. And I would like to go over some problems from 13.1, actually go over all the homework problems, and write down some of the formulas that are going to be needed for 13.1, and talk about them a little bit also, in addition to doing the problems. So we're starting off with, the things we're doing is simple interest and compound interest are the main topics. Also, future value of money and present value. Number one, Ernie Rawls deposits $5,550 at 2% annual simple interest for 1 year. How much interest will he earn? So we're just talking about interest that is earned, and there's actually a formula for interest. You could figure out how much money he accrues over the time, and then basically take that amount and subtract it from this starting amount. But we have a simple enough formula for this, so let's just use it. Number one, and that would be interest. This is simple interest, by the way. Maybe I should write that down. I think I will. I think I'll write down simple interest. Okay, so simple interest is just going to be interest is going to be equal to the principal, which is your starting amount, times the rate, annual interest rate, times t time. So we'll go ahead and put a little red box around that so you can refer back to that. And our problem was that the interest equals a starting value of $5,550. That's dollars. That gets multiplied by an interest rate of 2%, so 0.02. And it says they're going to leave this in the bank or whatever they're doing. What are we doing here? A deposit. So it's being deposited for 1 year. Okay, 1 year. So then when you just multiply all that up, we end up getting that the interest for that 1 year is going to accrue to $111.00. And so that is the answer. Number two. So number two is find the simple interest as well. So same thing. So let's figure that out. Interest equals the principal starting amount, which is $6,000. $6,000 times the interest rate, which is 6%, so 0.06, change it to a decimal. And here's the difference from the last problem. They're asking for 3 months. And if it's not specified, the simple interest is going to be just on default, is going to be annually. So if it is 3 months, that's in months. We need to be in years. And so, of course, 3 out of 12 now converts it to years, right? And that would be 3 months is actually a quarter of a year, right? Reduce 3 over 12 and we get 1 over 4. So it's a quarter. So what you could put here is the time is a quarter of a year. Of course, you can also use decimal, which is 0.25 as well. In any case, when you multiply 6,000 times 0.06 times a quarter is going to give us $90. And that is the interest. Now, number three changes it up a little bit. They're not just looking for the interest, they're looking for the future value. And so what that is basically doing is they're saying, okay, if you start with a certain amount of money, in this case, $1,800, and it makes 9% interest for 2 years, the future value of that is what it's going to grow to. Okay, so let's write down some formulas for you. The first one's going to be simple interest. So this is simple interest. Difference between the last one. Last one was just purely just the interest, but now we want to know the future value. So that makes the formula a little different because it's got to show the accumulation of the principal starting amount plus the interest. So future value is all of it that it grows to. So it's called future value. So future value for simple interest is going to be the accumulation, or the amount that you gain in the bank account is going to be equal to the principal, which is the starting amount, times 1 plus the interest rate times the time. Now our default is going to be always annually, and if it's anything different than that, they'd have to specify. Okay, so I'm going to put that in red so you can refer back to it as a formula. And let's do the problem. So on number 3, it's asking for the future value. So A, the future value. Remember, this is going to be our starting amount, our principal, and in number 3, first part, the principal was $1,800, and that gets multiplied times 1 plus the interest rate. Now remember, the interest rate, written as a decimal, 9% is 0.09, and that gets multiplied by the time, and I believe they said the time is for 2 years. So 2 years. Those are dollars. And when we multiply, now remember, when you do this, you have to, there is an, oops, I've showed another parenthesis. There is an order of operation thing that's going on here, right? You have to multiply first before you add the 1. So if you do this in the proper order, this piece right here is going to end up being 1.18. And then that gets multiplied by 1,800. And that gives us this total future value, or the total accumulation of $1,800, starting with $1,800, making 9%, and as simple interest for 2 years, you're going to have $2,124 and 0 cents. Okay, that's simple interest. Now the thing about simple interest that's interesting is that the amount of money you made the first year for simple interest is going to be, the interest is going to be the same amount every year. So it's actually just a linear growth. You're going to make the same amount every year. It's going to be 9% of $1,800 the first year, and 9% of that $1,800. It's just of the principal. The reason why I'm saying that is because when we do the second part of this problem, which was talking about compound interest, and this is also future value. So the thing about compound interest is that the interest, the percentage that you're growing by, the percentage stays the same, but the actual growth grows faster because it's compounding on itself. So on simple interest, you're taking 9% of the principal, so that principal never changes. It's that starting amount. Whereas in compound interest, you're taking, let's say, 9% of the pot that grows bigger and bigger and bigger. So because of that, it grows faster and faster, which is a exponential growth. But let's take a look at the formula for this. So it's going to be the amount equals the principal times 1 plus our interest rate divided by our compounding periods, raised to the compounding periods times time. And some books, in this book also shows this formula. It also shows another formula where they put an M here, and that's just the number of compound periods. But that's just going to be the compounding n. N is how many times it compounds a year, times t is how many years. So the compounding periods will be multiplying those two together. Let's put a little red box around that. And also I think that another thing we need to really kind of focus in on this problem is, let's make this red. Where are we at? So the second is, we want to find the future value of an account that pays interest that's compounded annually. Well, compounded annually means once a year. So that means our n value is 1. So let's put that down here. This is n equals 1. Okay. So when we go ahead and fill out our information, by the way, that means that this, oops, I just went to erase. That means that that is going to be 1 and that's going to be 1. But let's go ahead and show all that. So now what we have is the amount equals our principal, which is the same as before, 1,800 times, and I think I'm going to use brackets here, times 1 plus, what does it say? 1 plus our interest rate, which is still 9%, so 0.09, divided by our n, which is our compounding periods, and that is just going to be annually, so that's just a 1 there. And then it's raised to the n, which is 1 again, times how many years how many years? I think we said 2 years. So if you want to simplify this, you'd have to divide first, which is just going to be 0.09, and then add 1. So what this looks like is 1,800 times 1.09 raised to the second power. Of course, we always do exponents first before we multiply, so you have to do the exponent, 1.09 raised to the second power, and then after you did that, you would multiply. So I'm just giving you a little more information. We have 1,800, and when we took 1.09 to the second power, we get 1.1881. And then when we multiply that, we're going to get our approximate answer because we're going to round, and it's going to be about $2,138.58. They said round to the nearest penny. And so there's our answer. And you can see we made a little bit more money. Over here it was 124. This is 138. You make a little bit more money compounding. But really where compounding really shows up, where you really start making more money, is as you continue to do it. This is only 2 years, but if this was 40 years, you'd see a massive difference because the growth, the interest or the growth is building faster and faster because you're taking a percentage of a bigger pot of money, whereas simple interest just takes interest of that principal only, just looks at the principal. Okay. All right, well, let's move on to the next set of problems. Number 4. Well, another thing that I might I think I'll go ahead and talk a little bit more about is, since we've got COVID-19 and all this stuff going on, people talk about exponential growth with that. Let's see if I can get another page. So compounding interest is exponential growth, and simple interest is not exponential growth. Simple interest is linear growth, so it's the same amount. The interest is the same every year. So one example of exponential growth, and they were talking about this whole doubling idea. So I'm going to use a similar looking formula, but if I say A, the accumulation of money, if you want, but instead we could talk about, I guess, people in a population. And if we say we started with 10 people that were sick, and we say that the virus doubles, well, notice, I guess I should go back over here. Let me pull back over to, let's see. Notice these problems right here have 1.09. So if this base was 1 and you raised it to some time, a power, right, even to 20 years, it's just going to be 1. So if that base is 1, nothing changes. It's not exponential growth. But if it's bigger than 1, it's going to grow. And this is 1.09, so it's growing by 9%, but it's compounding. But if you're going to say something is doubling, it's not growing by 9%. Let me get to it. It would be doubling. Whoops, and then it changed to my eraser. Here we go. It would be doubling. So, if we're talking, then we'd have time. So this is what I'm talking about, how it grows faster and faster because it's compounding on itself. For instance, if we said, what would happen? So if we started with 10 sick people, and we said, how many sick people do we have after 1 day? And that'd be 2 to the first, which is 2 times 10, which is 26 people. So it doubled, right? Started with 10, and now we got 20 after day. And you can say, well, what happens? Oops, this darn thing changes to pencil or to eraser. What happens if we have 10 sick people and it doubles? That's the base of 2, okay? And what happens after 2 days? Well, 2 to the second is 2 times 2, which makes 4. And you can see after 2 days, we'd have 46 sick people. So we had 10, then we had 20, then we had 40. You can see doubling. It doesn't seem like that many people, but look at this. What if I just went and said, you had 10 sick people, and it doubled, and how many sick people would you have after 30 days? Well, 2 to the 30th power is a very big number. Then you multiply it times 10, and the amount would be, I think it's like 10,737,418,240. It'd be a lot of sick people. That's more than how many people are on the world. So it's definitely, COVID is definitely not, it's not doubling like some people were saying. It's not doubling, but it is exponential growth, and then it gets more complicated because then the curve starts flat. It's like exponential, and then it starts to, not become exponential, and it curves off and does this sort of logistic thing and gets a little more complicated. But anyhow, I wanted you to see that at the very beginning of this exponential or compounding interest, the very beginning, it's really not all that impressive, and it looks a lot like a simple interest. But as you go, this would be like, if you said 30 years in the COVID situation is only 30 days, but 30 of these compounding periods really grows a lot. So that's something to think about. All right, let's get up here to problem number what? 4? Problem number 4. There it is. So on problem number 4, what do we want to do? We want to find the future value of each deposit if the account pays simple interest, A, and then B, interest compounding annually. Now, something to remember when it's compounding annually are n equals 1, and it kind of makes our formula a little bit easier because you have some 1s in there. But let's start off with simple interest. And let me see if I've got some space to do this down here. This is going to be number 4, part A. And number 4, part A, we just looked at that, and that would be our formula for simple interest. Now this is find the future value. So this is not just interest, it's finding how much would accumulate the principal plus all the interest that you made. And once again, this is simple interest, so it's going to be that accumulation equals the principal times 1 plus the interest rate times time. Once again, that's our formula, so I'll put a little red box around it. And according to that problem, the principal happened to be $2,200 times 1 plus the interest rate happened to be 4%, so 0.04, and that got multiplied by how many years on problem number 4? Problem number 4 said for 5 years. Okay, so for 5 years. And once again, we are going to have to multiply first and then add. Okay, so if we do that in our proper order, multiply first and then add 1 to that, this would be 1.2. Then if we multiply 2,200 gets multiplied by 1.2, and we round to the nearest penny, we end up getting $2,640.00. And that is our future value of $2,200. That's our future value in 5 years, making simple interest at 4%. Let's do part B. Part B, remember, is not simple, it's compound interest. So compound interest is accumulation equals the principal times 1 plus the interest rate divided by the compounding periods, raised to the compounding periods times time. It's the same formula I showed before, but I just did it again. And let's fill in what we know. The principal is the same. It's the same problem, but it's now compounding interest. So it's $2,200 times 1 plus an interest rate of 4%, 0.04. Now it's the compounding periods, if you remember, I tried to do that in red already, is n equals 1. So of course, when we put a 1 into this problem, divide by 1 is not changing the value, and multiplying and rate. And so anyhow, you can see that it does simplify the problem a little bit. Raise it to the nth power. These two numbers are always the same. So that's still 1. And then time, on this problem, time happened to be 5. So multiply it by 5. So now we've got 2,200. We've got this stuff right here in the parenthesis that we just add, which we get 1.04 raised to the 1 times 5 is 5th power. So if we raise this to the 5th power and then multiply it by 2,200, we get that accumulation is approximately equal to $2,676 and round it 64 cents. All right. Now let's see what happens. Next one is oh boy, I'm running out of space. So number 5. See if maybe I can squeeze that over here because my space is tight. So Alex was late on his property tax payment to the county. He owed $5,024 and paid the tax 9 months late. The county charges a 7% simple interest. Find the amount of the penalty. So basically, we want 7% of the $5,024, but not for a whole year, a part of a year. So that's where we want to kind of dial that in. 9 months. Well, 9 months is 9 out of 12, right? And 9 out of 12, 9 out of 12 is going to reduce to what? It's going to reduce to 3/4, which is, if you want to use that as a decimal, is 0.75. So basically what we're doing is we're trying to find the tax of this, and it's going to be the same formula for just interest, simple interest formula, right? The simple interest formula was just the simple interest equals, in this case, since it's tax, let's call it tax, but the tax penalty is going to be, it's a tax penalty. I guess I better put a P there. It's just going to be the principal times the rate times the time. So what it's going to be is, it's going to be $5,024 times the simple interest rate, which is 0.077%. And we need to do this not for a whole year. Remember, it's 9 months, which is 75% of a year. So you could use 0.75, or you could use 3/4. Would get us to the same answer. So when you multiply that, the penalty is going to be, so when you multiply all this together, the penalty is going to be $263.76. That always, those penalties are such a pain because, if you paid it on time, you would have that money, right? So that's number 5. Check, we did number 5. Let's take a look at number 6. And I guess 6, I guess I didn't have to do that because 6 doesn't take as much space as I thought. It looked like it was. But number 6 looks like we're going to have to figure out compound interest, which takes some time and space. But they already gave us the final amount. So it really actually made this problem a lot easier. Find the missing interest earned. Okay, so here's what's going on. Here's your principal. And then, of course, interest rate compounded quarterly for 4 years. But then they calculated the final amount, right? That's what we've been doing. But they calculated it for us. So they want to know, what is the interest? Well, the interest is just going to be, so the compound interest, which actually is not the easiest to find by itself. But when you have all this information, it's really actually kind of easy. So your compound interest is just going to be equal to the, and let's do this with some color, I guess. It's going to be equal to this final amount. So it's going to be equal to this final amount minus your principal, what you started with. Okay, so the principal, what we started with was $1,025. And the final amount is right here, which is $1,407.11. And so once again, we've got this final amount minus the starting amount. So what's left when we subtract that? It's the interest. It's the stuff that we made, right? And so we subtract those two values, $1,407.11 minus $1,025, and we get $382.11. And that is the compound interest. All right, that's number 6. Number 7. Number 7 says, interest is compounded semi-annually. That's something I need to point out right now. We got to get the language down, that when it says compounded annually, n would equal 1. But when it says compounded semi-annually, that happens 2 times a year, right? So n equals 2. Semi-annually means 2 times a year. Okay, so what was that formula again? Well, I'm just going to write it down again, just to kind of hammer it. Remember, this is, so once again, this is interest compounded semi-annually. Find the final amount. So when you're finding the final amount, that's another way of saying future value. So the final amount or future value of this money is going to be the same formula I had before, which is amount equals principal times 1 plus the rate divided by n compounding periods raised to the n compounding periods times time. Once again, that is our formula. Let's put these values in here. The accumulated amount, or the future or final amount, when you have a principal starting with $3,000, and then we multiply it by 1 plus the interest rate, which is 0.05, divided by our n value, which is semi-annually, so n is 2. But what gets to happen here is we raise it to the n times the time. Now, what's the time? 3 years. What is the n value? How many times does it compound a year? 2. So I'm simplifying this. Of course, order of operations inside the parentheses, you're going to have to divide first, 0.05 divided by 2, and then add 1, and that would give you 1.025. Of course, 2 times 3 is 6th power. And then you need to multiply that. So the next thing you need to do is get a calculator that can do the 6th power, and very often that calculator, you would use this caret key for exponents, or x to the y key button, or some calculators have y to the x key button. It depends on the maker of that calculator. Okay, and some of the new ones have these little keys that might have an x and then show a little cursor right there. So you have different calculators do it a different way. This is a little more old school right there, but you need to be able to get to a 6th power. So 1.025 raised to the 6th power, get that value, then multiply it by 3,000, and we will have our answer, and this is going to be approximate. We have to round it to the nearest penny or cent, and so it's going to be the future value of $3,000 in this situation is now going to be $3,479.08. And that's your final amount. also known as the future value. Okay, let's take a look at the next one, number 8. Interest is compounded annually. Okay, let's use a little red there. Interest is compounded annually. That means that n equals 1. Okay, find the final amount in the account and the interest earned after the given time. So I don't think I'm going to write that same formula. I've done it many times. That's the same formula right there because it's compounding interest. It'll end up being a little simpler in the way because n is just compounding annually, so that'll just be a 1. But let's put our values in. So the future value or the final amount is going to be equal to the principal starting amount of $6,300 times 1 plus an interest rate. Now this interest rate, everybody can see it says 5.5. I'm going to write it as a decimal because when we change it to this is a percent with a decimal, we change it to a pure decimal, we have to move the decimal point to the left 2 places and drop the percent sign, right? So this is going to be point, right, there's one right there. 0.055 is what that 5.5% amounts to as a decimal, divided by our compounding periods, which was just 1, which is very easy to deal with. And then that gets raised to 1 times the time, which was 24 years. All right, well, this should show some really good growth because now we're compounding it for 24 years. That should show quite a bit of growth in our account. So, of course, the first thing you do is divide. Divide by 1, which doesn't do anything, and then add 1. Okay, so this value in the parentheses is 1.055. 1 times 24 is 24. Now you really definitely need to have that exponential button, like I just talked about in the last problem, maybe a caret or whatever. We need to type in 1.055 raised to the 24th power, enter, then multiply it by 6,300, and we get this accumulated amount. And actually in this problem, I guess I showed a little bit more detail. I showed a little more detail just in case you're sort of struggling with the calculator. What does this amount to? Well, it amounts to about 3.614589904. It keeps on going. You just want to leave that in the calculator, right? Don't erase it. Don't type that back in. Just leave it in and then multiply it by 6,300. And now we round it to the nearest penny. And we're going to get, oh, look at that. So this is why compounding interest is called, I can't remember the quote, the 8th wonder of the world, something like that. So here's the beauty of it. Look I started with $6,300. And if I just let this money sit for 24 years, 5.5% is not extraordinary. No. Anyhow, let it sit for 24 years. And now I have $22,771.92. This is great. Let the money work for you. Okay, that is the final amount after that given time period, also known as future value. Okay, now this is going to take some work here. We're trying to find compound interest with these different given compound periods. So here we go. I'm going to go ahead and specify each one because this is really everything else is the same other than the compounding periods from problem to problem. This particular problem says compounding semi-annually, so you guys know that means n equals 2. This one says compounding quarterly. Quarterly means it happens 4 times a year. Compounded monthly. This n value now is, well, how many times does a monthly happen a year? 12 times. Compounded daily. Whoa. Now that is a lot of compounding periods once a day. So in a year, it's 365 compounding periods. And compounding continuously. Yikes. Now that sounds impossible. How could you compound continuously every moment of the day? And really gets into looking at the limit of our formula And I'm not going to go into that much detail, but you notice with our compounding interest formula, you've got this piece that says 1 plus the interest rate divided by n raised to the nth power. Of course, there's also time, but if you just kind of focus in on that piece right there, it turns out, in fact, let's put a 1 there. It turns out when n gets extremely, extremely large, it becomes this really special, cool number called e. And you have to be able to find that on the calculator. On many calculators, you have to hit the shift button, which is maybe blue or yellow. And most calculators have ln, which is the natural, which is the natural log button. And e is its inverse, so e would be like right there. So if you want to activate this e as a base, which that we will want that for this continuous formula, you would hit shift and then you would hit this button, which would activate that. But like I said, every calculator can be slightly different, and so could be slightly different. So you have to look at your calculator. But because all of this machinery, or however you want to say this function, as n gets super large, well, if n is large, that's continuous. That's that continuous idea. It sounds like our formula is going to get really challenging and hard, but it turns out because of that e value and that limit, the formula for compounding continuous, which is compounding every instant of time, I guess you can call it that way, the formula actually gets easy. It's going to be the principal. It's going to be the principal times this e value, which is actually a number. It's not a variable. And that gets raised to the rate times time. And so a complicated formula, actually, complicated procedure, actually, because of mathematics, we're able to boil it down to that easier. This is future value of money that's being compounded continuously right there. So when you do that one, that's the formula we're going to use. But the rest of it is the same formula we were using before. Let's do this by labeling it as, let's label this as semi. So semi-annually, and we already noted that means that n equals 2. So we're doing this first problem right here. And what does that look like? Well, it looks like this. The future value of that money, if you start with, now the particulars here, right, is that you're starting with $1,025. Annual interest rate is 6.9% over 3 years. And then what's changing is these compounding periods. So if we're going to do this semi-annually with a compounding period of 2, it's going to be $1,025 times 1 plus that interest rate we saw back up there, which was 0.069. We are going to, it's being compounded semi-annually, which means twice a year. And then we are going to have to raise it to the compounding periods. Remember, those two numbers are always the same. That's why I'm making them red. Times the time value or time interval, which was 3 years. Okay, simplifying this, we're going to divide, we're doing order of operations in the parentheses, so we have to take 0.069 divided by 2 and then add 1. Well, that amounts to 1.0345, and that's being raised to the 2 times 3 6th power. Continuing on here, I think I'll put this down just so you can see it, but 1.0345 raised to the 6th power is about 1.2256965 dot goes on, forever. So anyhow, when we multiply that, we can get the approximate value, round it to the nearest penny, and that gives us $1,256.34. Now that is the accumulated amount, but got to be a little careful here. It says the interest earned. Whoa. They want to know the interest earned. So the interest earned is, well, we can figure out the interest earned is going to be the accumulated amount. And then we need to take away what? We need to take away what we started with, the principal, $1,025. Because the final amount, the future value minus the starting amount, well, that gives us the interest. So if we subtract those two, we would have $231.34. And that is the answer we're looking for. That is our interest. Interest that was earned. So they're just basically trying to go through here and showing us that the interest earned is going to change if you have, more compound periods. You gain more. Now, really does it is if you have more compound periods and you have more time also. That's what really distinguishes it. So I wish they would have had a bigger number than 3, but they don't. Next one is quarterly, and I hope I have enough space for all this. Next one's going to be quarterly. So let's write quarterly. What do I mean by quarterly? Look at it says find the interest earned if the interest is compounded quarterly, right? So that's when n equals 4. So let's go up here and say, well, n equals 4. And we're going to use the compound interest formula, which is just the accumulated future value is A equals the starting amount, 1,025, times 1 plus that interest rate, which is 0.069, divided by, now this time, compounding 4 times quarterly, right? And so we put our 4s in the proper spot, and it's raised the 4 times time. The time was 3 years. So first divide by 4, then add 1. That's our order. And when we do that, that gives us a 1.01725. 4 times 3 is 12th power. So we now need to raise it to the 12th power and then multiply it by 1,025. And that'll give us our approximate accumulated value, which is $1,258.51. But remember, they wanted to know, they weren't asking for the accumulated amount. They're asking for how much interest, compound interest, did you gain. So we better subtract out what we started with, 1,025. And when we subtract out what we started with, we'll have that interest gained. Okay, so that is going to be quarterly. So this is going to be $233.51. And that's our interest. So you can see that number should be going up a bit, not incredibly. 231, 233, yeah. Next one, I'm going to try to sneak this in here because I need more space over there. This next one, I believe, was monthly. And of course, it just, okay, there we go. Monthly. And of course, monthly means that the n value is 12. Here's our setup. So we're starting with $1,025. Multiplied by 1 plus our interest rate, 0.069, divided by our compounding periods, which happen to be 12, raised to the 12th power times how many years? 3 years. So what does that look like? That when I divide by 12 and add 1, I get 1.00575, which gets raised to 12 times 3 is 36. And we raise the 36th power, multiply it by 1,025, and we end up getting this accumulation is about $1,259.98. Of course, that's the future value. They wanted to know what's the interest, what's the compound interest that was gained. So we got to subtract out what we started with, 1,025. And I'm sure there's probably another formula for this, finding compound interest, but this is one of the easy ways just to, keep our formulas to a minimum. Anyhow, so we've got this future value. We just subtract out the principal, and we end up getting an interest of $234.98, which is the answer to that. I'm running out of space, so I'm trying to squeeze all this stuff in. Here we are. We just did monthly. Now we're doing compounded daily. So daily. Of course, with daily compounding periods, it happens 365 times a year. So what is our problem? The amount equals, starting amount 1,025 times 1 plus interest rate 0.069 divided by my compounding periods, which happen to be daily, so 365 of them, raised to the 365 times how many years we're doing this for? 3 years. So, we're going to have to first divide, and then add 1. Order of operations, that would give us, not the nicest base here, 1.000189041, and of course that goes on and on. And then when we multiply 365 times 3, we get the raised to the 1095th power. And once you get that, multiply it by the principal, and we get our approximation to be about $1,260.71. That would be the accumulation or the future value of that situation, but they asked for the interest, compound interest that was gained over that time period. So we better subtract out, what was that? We better subtract out our principal, $1,025, and when we do that, we get that interest gained. That gives us $235.71, which is the interest. Whoops, what happened there? That was weird. Okay, I guess I got to try that again. I was just trying to box the darn thing. It's the easiest thing in the world. There it is, okay, and then that's the interest. Whew, what a workout. Now the last one is going to be compound continuously. That is when our end period goes to infinity, right? It's every instant of the day. It's kind of a weird idea. Sounds almost impossible to do, but we end up getting this simpler formula as long as we can find the E button on our calculator. It is the future value compounded continuously is going to be the principal times E raised to the rate times time. Let's put a red box around that for our formula so you can go back and find it. And let's do this thing. Here we go. We're almost out of space and time. The principal is $1,025 times E raised to the rate, which was 0.069, times the time, which was 3 years. So you're gonna have to raise this. You're gonna have to find that E button, and I was showing you, how you can do that. Most calculators you're gonna have to hit the shift button, and then usually you'll see ln, which is the natural log, and its inverse is e. And so you need to activate this inverse e to the x, which is this e. You type the e to the x, and then you type in this exponent. Is how most calculators these days work. If you have something super old, it gets dicier and harder to input. So e raised to this power, of course you could write that as a multiplication problem on most modern calculators, but put parentheses in it so it knows that all of that should be in the numerator. And just so you could kind of follow along because you might be new to using that button, what should happen here is this stuff, let me use some color here, purple, sure. This stuff right here, when you put it in the calculator, should be approximately 1.2299825. 82572, and that's quite a bit of accuracy there. Now we just multiply those two values and we've got the future value accumulation, which is approximately $1,260.73. That would be the future value, but they asked for the compound interest. So we better subtract out the principal, the amount we started with. And now we're going to have, these are dollars, now we're going to have the interest that grew, $235.73. That's supposed to be a 5 there. These are dollars, and this is interest. And since that's compounded continuously, you can see that is the biggest growth. 235 is bigger than all of the other ones. Not much bigger than compounding it daily. 235 and 71 cents. Oh boy, $2.235 and 73 cents, 2 pennies more. But as I said, over time, it does end up being a big difference, especially between continuous and compounding just annually or semi-annually, where you're just doing it once or twice a year. Okay, let's move on. We're getting there. Whew. Okay, we have a change in question here. What we've been doing is finding future value, and now we need to find present value. So there's a different feel. The thing about it is it's the same darn formula. If we don't want to make a new formula, we can just use the same formula. But let me go ahead and give you that choice. The same formula is that we've been using for future value is the amount equals the principal times 1 plus the interest rate divided by the compound periods raised to the compound periods times t. And the difference or the difficulty here is if you're trying to find let's use color here. If you're trying to find the present value and not the future value, the present value is going to be p. And the future value is going to be what it grows to, a. So if you use this formula, you would just put in everything else except for the p and then algebraically isolate p. But some of you guys probably, some no problem and some it's going to be a problem. So let me just isolate p for you right now. And so we'll have a new formula where p is isolated. So then you just plug in value. So here we go. Let me do this for you. Let's go ahead and make a new formula. It's really the same darn thing, but it's just manipulated a little bit. So let's see, algebraically, this is bonded with a multiplication. So how do I get that stuff out of there? Because I'm trying to get p by itself. Well, I would, and let me use another color, I would divide by that big old factor, all that nasty stuff up there, which is 1 plus r divided by n raised to the n times t. It's identical, and when you have same exact factors, you get to cancel or reduce those factors. If I divide the right by that, I must also divide the left by that same value, 1 plus r divided by n raised to the n times t. And we have ourselves a formula. Let me rewrite it and clean it up. So if you want the present value, you're going to solve for p. So you're not going to put in a value for p, but then the rest of it's just going to be you're going to put in the future value that you're trying to get to, divided by 1 plus r divided by n raised to the n times t. And that is your formula. I guess I put formulas in red. So this is your formula for present value formula. What is this good for? It is good for planning ahead, meaning what kind of money do I need to start with in order to get to a certain goal? Okay, that's what they're asking on number 10. Let's do it. Find the present value of the following future amount. So if I want to have $4,000 and I know I can make 8% on it compounded annually, and I'm going to do this for 20 years, how much money do I need to start with? That's the question, right? That's the question. Okay, so $4,000. Okay, well, let's do it. Number 10. And let's just go ahead and use that formula to get used to it. P equals the amount. So this, once again, is your future amount, the goal that you're shooting for. And this is your present amount that you have to start with to make that goal happen. And then the rest of it, 1 plus the interest rate divided by the compounded periods raised to the compounded periods times time. So what does this look like? My principal, you could think of it, or your present value money, your starting seed money that you start with. What is it going to be if I want to have $4,000 in the future, right? So what's my present? Let me use the right language so it makes sense. What's my present value? What's the present amount of money that I need to get to $4,000? My goal. And that's divided by 1 plus, and they're telling us if you're making an interest rate of 8%, so that's 8%. Compounded what? Compounded, I like to use red for those. Compounding, what does it say? Compounded annually. Well, compounded annually means n equals 1. We like that because that means you put a 1 there and you put a 1 up there. Makes it easy for calculations. So compounded period 1 and 1, and then what's the time of this interval? 20 years. Okay. Some reason that just doesn't, it doesn't quite seem like, let me think about that. So 20 years. So anyhow, here we are at 4,000. We're trying to get to 4,000. What's the present value? Let's see. Let's simplify this. This is going to be 4,000. And down below, we're going to have a 1 plus 0. I'm sorry, we're going to have 1.08 raised to the 20th power. And let's go ahead and do that problem in the on our calculator, and we get approximately the present value, $858.19. So that's the language there. That's your present value. That's what you need. Present. So you need $858.19 in order to have $4,000 in this situation. Okay. All right, let's do the next one, number 11. So number 11, find the present value of the following future amount. Okay, so in this case, something to pull out right there is compounded semi-annually. That means that n equals 2. We've got, now remember this is a future amount. That means this is your A value, is $5,000. Okay, let's do this. Present value that we need is going to be equal to this future value of $5,000 divided by 1 plus interest rate of 9% divided by compounded semi-annually, so that has to be a 2, and raised to the 2 times in how many years? I didn't see how many years for 20 years. Okay, so that's going to be 20. And so then when we do the math here, and I think what I'm going to do is I'll give you that approximation. What does this denominator become? It becomes approximately 5.816364,538. Right, just leave it in your calculator, then divide it, and we get that approximate present value is $858. $59.64. Okay, number 12. Number 12. What's our final thing here? So we've got Tinja wants to establish an account that will supplement her retirement income beginning 30 years from now. So 30 years is our time horizon. Find the lump sum that she must deposit today so that $5,000 will be available at the time of retirement. If the interest rate is 11%, woof, I'd love to get that. Compounded quarterly. Okay, compounded quarterly, that would be n equals 4 there. All right, let's do it. This is definitely a present value, meaning how much money do I need right now to throw into investment for 30 years to make $500,000, $500,000 compounded quarterly at 11%. Well, let's see. How much money do I need right now? Okay. It is going to be the A future amount, $500,000, $500,000, divided by 1 plus 11% divided by, it said compounded quarterly, so that's got to be a 4. Of course, that little 4 goes in the exponential spot as well and gets multiplied by how many years? 30 years. So, 500,000 in the numerator. When we do all this stuff here, we get a base of 1.0275. And when we multiply that, we get it raised to 120. And then we put that in the calculator and we get approximately, how much money you need to start with? You need to start with $19,281.92. If you start with that amount of money, in 30 years, you'll have $500,000. Yay! And you can retire in luxury, kicking back, allowing that $500,000 to continue to generate money. And so that you probably just live off that interest and just, that's the dream, right? Let that money work for you. Okay, I hope everybody is doing fine, healthy, COVID-free, and got something from this long, I don't know, not lecture, but kind of lecture. I decided to try to fill in some blanks for you guys and have those formulas at your fingertips. Okay, signing off here. Take care, and I hope you have a great rest of the day.